externalized Genesis sequence.
Hello, welcome everyone. Here we are talking about my favorite subject again. So this is, hopefully we have some good news. This is something that we've been thinking about for quite a number of years, and most recently Victor has been working hard at for the last year and a half or so. And so hopefully we have some good news about our old friend. So people say a lot of things about Java serialization, and most of them are true. Java serialization is, it's both amazing and horrifying, right? And so you could characterize it as a big mistake, and that you could make that argument. You could also characterize it as Java would have never succeeded without it, and I think you can make that argument as well. But certainly, given the amount of the number of times that I have to make jokes about serialization to sort of metabolize the pain, it does sort of show that it is the gift that keeps on giving. So I vote for all of the above in this list here. So serialization got added to Java in 1997, which was with Java 1.1, and it was it was not something that was on the roadmap in Java 1.0, but it was something that came in very quickly, and there was a great deal of urgency to get it in because it was known to be very important that we wanted to be able to transparently persist and persist Java objects and send them across the wire, store them into databases. And this is sensible concept. The need was real, and the historical context was, distributed objects was the big thing, right? Like the best-selling technical book in 1997 was this awful book called the Distributed Object Survival Guide, which was like the rewrite of the Corba Survival Guide. But that was the hot buzzword. That's what everyone thought the industry was going. So of course the design that we got in 1997 focused on distributed objects, taking an object, moving it from one machine to another, and we just didn't quite realize or want to realize what the implications were. So my friend and colleague John Rose likes to say, they're cute when they're small, right? So if you look at the original design for serialization, you think it's okay, it's this cute magical lizard, and, you get rainbows and butterflies, but eventually those cute little lizards grow up, and they're not quite as cute. And in fact, Stuart said to me, well, that alligator actually still looks kind of cute and friendly, so we had to punch it up a little bit. But it's definitely something that seems harmless until you realize just how harmful it can be. So about 5 years ago, after I got fed up with some conversation I was having over and over again, I decided to write up exactly what it was that I hated about serialization, all the things I hated about serialization. I think this was an elaborate nerd snipe on the part of my friends who figured, yeah, if we get Brian riled up, we'll get him to write one of those great papers, and it worked, I guess. I'm not going to summarize the paper for you. You can go read it. It was fun to write. It might be fun to read. But it identifies a lot of questionable moves in the serialization design and why that causes trouble. And like I said, I won't go through all of them, but I do want to go through this one here in red, which is probably the most appalling one, which is adding serialization to the language the way it's been done takes all of the mechanisms in Java for maintaining the integrity of the object model, like accessibility and objects are constructed with constructors, and throws them all out the window. So for a class that uses encapsulation correctly, you can read the code and reason about what state instances of that class are going to be in. If a class is serializable, you can't reason about what the state might be based on reading the code. Just think how appalling that is, right? So it takes all of the great things about Java, about creating safety, creating integrity, and tosses them out the window. So you might have been here probably in this room about 5 years ago, and Stuart and I got up and gave a talk about it. We summarized what was in the paper. We talked about some ideas about how we might improve it. And we've been hard at work refining those ideas and implementing them. So just to summarize very quickly, what is so wrong with serialization? The biggest problem is that it's magic and it's extra linguistic, which is to say it doesn't use the features of the language. So it doesn't it doesn't extract the state of an object by going through its API. It just scrapes the memory directly. It doesn't deserialize objects by calling constructors. It just creates blank memory and scribbles all over them. And you know, as a bonus, it's this big packed monolithic thing that combines graph walking, state extraction, encoding, wire format, decoding, and reconstruction in one go. And you know, if you want any of those, you have to take them all as they go. And as a bonus, it's also just really hard to use. And a lot of people, you know, say kind of like smugly, oh, well, I don't have a problem. I don't use serialization. I use Jackson or Cryo or Avro or Thrift. But I have news for you. All of those systems have all of the same problems for all of the same reasons because they're using all of the same flawed mechanisms. So if you were at my keynote this morning, I talked about my peak of complexity model. And serialization is definitely an example of shipping the peak of complexity solution. And we've been living with this peak of complexity solution for 30 years. In fact, we've been spending a good chunk of the last 30 years just trying to fix the most egregious mistakes that were made by shipping this peak of complexity solution. And there's been many hundreds or thousands of hours, painstaking hours that have gone into remediating security bugs and closing down holes and characterizing security flaws. And it never ends. There's no end of that in sight. So, serialization is definitely a feature where we ship the peak of complexity solution, and we've been suffering for it mightily. So, I'm going to talk a little bit about where the language has been in the last couple of years as a sort of foundation, and then Victor is going to talk about how we're going to use these, use these new language features to offer a potentially better way to solve the problem that serialization solves. So, here's a fact about how many people here use records. Okay, how many people know that when you have a record that's serializable and you deserialize it, it actually goes through the constructor and checks the invariance? Okay, probably about a quarter of the people who raised their hand the first time. So this is really cool, right? When you deserialize a record, it goes back through the constructor, and if your constructor defends the invariance, you will be protected against maliciously constructed streams because the constructor will see that's not a valid instance of this record. So the job of the constructor in an object-oriented system is to ensure that objects are created in a valid state. So for records, we revalidate those proposed components that come out of the stream at deserialization time. And as a bonus, we use the same constructor for both ordinary construction and for deserialization. So if you have to check invariance, you only have to check it in one place. And you don't have two versions that can get out of sync with each other. The current serialization story makes you do it in two different places with two different programming models. And nobody's ever going to get this right. It's impossible. So records are cool because records come with a semantic constraint that says, this record just is a carrier for its state, and that means I can derive constructor deconstruction pattern from the state description. Records are deconstructible through patterns, which allow us to recover the components of a record easily. For most of the features that records get, like you get a constructor for free, you get an accessor for free, you could write the code explicitly, you just don't have to. We can't yet do so with patterns, but we will eventually be able to, and I'll show you an example of that. But first, as a reminder of what I'm talking about, if I declare a point record, and I create a point, and then I pattern match on it with the point record pattern or deconstruction pattern, what that does is it breaks the point back up into its components, and then I can do something with it. One of the things that I can do is turn around and reconstruct the object. So this example here, point P2, is really like a clone operation where we say deconstruct the record with its pattern and then feed the bindings produced by the pattern back into the constructor. And you might think that's stupid, but if you think of this as sort of like the two pieces of bread, you can start to put interesting things in the middle of the sandwich, like serialize the components and send them across the network and reconstruct them on the other side. And this is our approach for making serialization more well-behaved. So we call this a record pattern or a deconstruction pattern. In the future, we'll be able to write these for any class. So I'll walk through how it works in a point class. So I have a point class, I have my fields, I have the obvious constructor. The constructor takes some arguments as inputs and then copies them into the record fields or into the record state. Similarly, so what the body of the record does, all it does is copy the arguments into the record. Similarly, I could declare a class pattern, deconstruction patterns for point, and the way you read this is actually backwards. What looks like the argument list are really the outputs. They're the pattern bindings. So this says, I have a pattern, it can match against points, and it produces bindings called X and Y. And what does the body of it do? Well, all the body of it does is read the object state and then say, yes, I match points. Here are the appropriate bindings. And the fact that these two things have the same shape, and one has the values coming out and one has the values going in, allows us to take something apart and put it back together. And that's the key thing that we need for better serialization. So there's been a couple talks here at Devoxx on pattern matching. There was one that you missed in the two sessions ago that Aglos did. And Gavin will also talk quite extensively about pattern matching in the Java Language Futures talk on Friday. So, and with that, I'm going to hand it over to Victor, who's going to solve all the world's problems.
Thank you, Brian. No pressure at all. So let me add some more information around the situation with serialization. So if you attended Stuart's talk earlier, we have this solution that attempts to essentially teleport objects. So taking an engine, making it appear somewhere else, still running. And clearly, that sounds really powerful and useful, but it also introduces quite a bit of problems. So one of them, or one of the main ones, is if you have a cyclical graph that you're going to try to send over. And please do watch Stuart's presentation from earlier today, because it really goes through this in depth. And serializing or deserializing objects through constructors, they sort of require them to be logically acyclic. Sometimes physical cycles might be okay, but sometimes you just have a domain object that has a completely different type of identifier. So having the object identity being the most important identity is sort of weird in that case. And it's also important to note that some of the most successful wire formats do not support cycles. And of course, there are some more grievances. So with serialization, it's using an interface, a marker interface, to say that this thing is serializable. That sort of dooms all subclasses to also be serializable. So you cannot necessarily know whether you're serializable or not unless you've checked whether any of your parents are also serializable. And also, if class C is serializable, then you have a part of your hierarchy which is serializable, but the other part isn't. So let me look at what does it look like? Well, clearly we do have a mirror situation. We have some application where we are going to create information and send to somewhere where we're going to receive information. So in both of those ends, we typically do have some sort of class. Could be different languages, of course, but just presuming that we're still within the Java domain here. So we have the class present on both locations, and here is serialization today. So you're working with your classes and your objects, and then you hand it over to serialization, and you don't necessarily know what's happening inside. It's very opaque. So you have the object input stream and object output stream, of course, but that's sort of where the information ends. So how do we descend from this sort of peak of complexity situation? Well, I think the first thing is to try to divide up some responsibilities here to just make the picture clearer. So clearly, the developer who is in charge of defining the class needs to have its logical area of responsibility. But we also have a different one, which is how do we extract information from what that developer decided to extract, and how do we represent what we extracted? And the same thing on the receiving end, we need to be able to receive that structural definition of the data, and we need to be able to turn that structural definition into the actual thing. So we need to unpack it. And of course, we want to go through constructors or factories or something which do have validation, so that we're sure that we create these objects in a known good state. So what's interesting here is that now there's only one thing left in the picture, which is the actual wire format. And if we have divided it like this, then now we have a clear place to plug in whatever wire format you want. And even more interestingly, we haven't even talked about I/O. So we don't need to know what the actual wire format is going to be, and we don't necessarily know whether it's going to have to go through files or sockets or just plain in-memory I/O. This is a key takeaway here. So what we're trying to do here is to make sure that the class author, the developer that declares the class, maintains the class, is in control over the external representation of that class or instances of that class. And that also means that that interface or that contract needs to be something that you design as a part of being a class author or class maintainer. You need to be able to have that control because things change over time, and you don't want it to be implicit because then you don't know when it implicitly breaks. So how do we define structural data? It turns out that it's sort of right in front of us. We're using parameter lists all the time. Parameter lists have an order, they have types, they have names. It's a pretty decent way of describing what the structure of something is. And of course, we need to be able to go from a structural representation to an object instance. And we already have that. We've been working with this forever. Constructors and static factories. Nothing magical about that. And what's interesting about them is that they both have these parameter list shapes. So going from the object itself to structured data, as Brian showed you before, if we have pattern matching, then we can clearly go from an object to its structural representation. And that also has a parameter list. So now, if that shape becomes the external contract, that is sort of the summary of that object as data. So one of the objections to serialization is that it's extra-linguistic, right? It uses mechanism that the language doesn't define. So what is the remedy there? Well, I think we should just use language constructs. That would be a good way of dealing with that problem. So what does that mean, or what does that look like? So in the example of the point class, what if we just told something that we intend for this constructor to be used from external sources? It's just a declaration of intent, saying that this constructor is fine, it's designed to be able to be used from external sources. Same thing on the other side. When you deconstruct an object, you could just declare that this is completely safe and intended to be used for this purpose. So in this case, and of course, naming is always difficult, and I'm not sure whether these are the, the names that end up, but for all intents and purposes, the unmarshaller annotation here just signals that use this constructor when you want to unmarshal something, which is take the structural representation and creating an instance of this class. And marshaller, of course, is the other way around. And of course, as you saw before, we just do a run-of-the-mill standard pattern declaration. So we call this any constructor or factory method annotated with an @unmarshaller, a designated unmarshaller. And the signature, or the parameter list plus the type, is what we call a schema. In this case, it's an unmarshalling schema because it's using an unmarshaller. And on the other side, on the pattern side, we have a marshalling schema. And the entire thing here is called a designated marshaller. And of course, the interesting thing here is this. So if you want to be able to take an object, as Brian showed you, if you create a point, switch over the point, pattern match on the point, and then create a new point, you need to be able to go from instance to structure to instance again. And then your signatures need to match. You need to be able to produce the information that you're going to need to consume. It's not all cases where you need this or want this, but most cases probably, because it's rare that you just want to marshal something but never unmarshal it on this specific application. But of course, there could always be use cases where that's not necessary. All right, another grievance. So looking into an object and scraping the field values out is an access violation. It wouldn't be possible in the language specification, but it's possible for serialization because it has these extra linguistic capabilities. But how do we get around that? Because sometimes the type is private, protected, or otherwise not accessible from the calling context. Or you might have a constructor that is unavailable or not reachable or accessible, or the pattern, of course. Well, it turns out it's fairly simple to just let the class author to say, hey, it's fine. You can look at my protected or private constructors and deconstructors. And I will allow to expose these signatures for the purposes of marshalling. But it's an opt-in, right? You're not accidentally exposing state or signatures that you didn't intend to expose. So this is real key here because the class author is in control. Also turns out that using language construct is fairly what we used to do, right? So if you had a point and you used to have a constructor that took a long and you encoded the two coordinates within that long, and you decided that this is no longer the way that we're doing it, deprecate it. It's fine. It's an old version. Just as an old version in code is the same as an old version represented in a file somewhere. So now you can just declare your new preferred unmarshaller for this type, which is separating the x and the y. So you can have any number of non-conflicting unmarshallers. Sorry, yeah, question?
We used to have a serialization UID.
Yes. So what's the question around? So the question is, we used to have a serial version UID. What about that?
Because deprecated has no version.
Yes, deprecated has no version. So the thing is that a version number only has meaning that you give to the version number. But if you have the structure, you could imagine that you have several previous versions of the same class. And they can still, given the circumstances, sometimes you have an incompatible change. But imagine that we were to introduce a new field. Are you able to provide a default value or not? So in those cases, you can actually just call the other constructor with the default value and silently upgrade the old version to the new. But of course, there's always going to be situations that you have where you have an incompatible change, and now you can decide, okay, so do I throw an exception? Do I log here? How do I deal with this problem? But it's in the control of the developer. It's not buried deep within some serialization functionality. And then for the patterns or the marshallers, you can have at most one, because that is the canonical current way to expose this instance as data. All right, so pardon the puns, but if we want to make a great point, we introduce a magnitude. So this is the example of, oh, this looks nice and all, but you haven't really shown any inheritance hierarchies. So how does this work when I inherit from something which is marshalable? So in the case where you have a typical class, the only difference here is the @unmarshaller at the end of that method, right? You would still need to call the superconstructor, provide the information. You would still require the information that the superconstructor needs from somewhere if you can't make it up yourself. You would still have to expose that in your signature. And of course, you can do your own validation and your own assignments. And this is just what we've done for 30 years. It's just delegating to superconstructors. And on the other side, and I think the important part is the syntax in progress here, we'll see where it ends up, but that's the inverse of this. How do I get the data that I need from my parent class? So in this case, we match this against the pattern we defined in point to get the x and the y out, because sometimes they're not accessible even from subclasses just by accessor methods. So you can actually get the data out of your parent and provide that when you represent yourself. Does that make sense? They're just inverses of each other. All right. So under the banner of use language features, we had some design choices to make. So one is use annotations to signal intent, which I think is a really good use for annotations. This is something that is basically what the code you would write anyway, but with another signal saying that, hey, this is intended for this use case. We use constructors and factories for instance creation, what we've done 30 years. No extra, no new stuff there. We use deconstructor for structure extraction, and we didn't necessarily have that before. And a key feature there is the targeted ability of extracting information at different levels in the hierarchy. So if you, as you saw in the previous code here, being able to targetedly look at point as one part in the hierarchy and getting the information out from that specific part of the hierarchy, that's a key feature here. And of course, you understand how that transitively translates down a hierarchy as well, because if point had a superclass as well, it would just delegate up to that, etc. So it chains nicely, just like constructors. Key thing here as well is let the class author be in charge. Very little in terms of providing magic. I think control is better here. And of course, there is a bit of a caveat here, right? So if we're extracting information, then we better make sure that it's either immutable or that we safely copy it, as always, right? So whenever we expose data that could be modifying the internal of our thing, we better either make sure that they can't be mutated or that it's a copy so that the mutation is safe. And the benefits here are quite many, right? So if we didn't have serialization and we only had this, then we wouldn't have transient, we wouldn't have serial version UID, serial persistent fields, read object, write object, blah, blah. You see, like you can't even see the entire list. So another thing was that it's monolithic. Serialization is monolithic. And the remedy there, as I talked about before, is to decouple the concerns. So I've shown you how you define a class which is marshalable. And here is an example on how you would actually turn an instance into the structural representation of that instance. And it's two key methods here. It's marshal and unmarshal. And marshal returns a marshaled of point in this case, and unmarshal takes a marshal of point and creates a point. And of course, these two at the end shouldn't be the same identity. They can if it's using a factory that has cached the instance somehow, but the important part is that they are equal. Then they are correctly implemented so that you can go back and forth. So when you call marshal here and provide the point, marshal is going to look and see, okay, so this is the point class. I'll look into the point class and see, are there any marshallers in there? I will take the one that is the canonical one because it's at most once, right? I will run that and I will produce a marshaled of point. And I will show you what marshaled looks like in a second. So marshal is the structural representation of P. And of course, on the other way, this is just inverses. Like this is just things and inverses over and over again. And the important part here is that we get a point which is equivalent to the one that we started with. So when we do this, what kind of information do we get from a marshaled? So a marshaled instance has a schema that I talked about before. You know, the parameter lists with the order, with the types and the names. So the owner here is the owner type. This is point in this case. And the parameter count is 2. And we have 2 ints as the parameter types. And we have x and y as the names of those parameters. And then we have parameter values. In this case, we're using immutable lists to represent the actual values that we had. In this case, we had 1 and 2, so x is 1 and y is 2. But you could see how this metadata around the marshaled point can help transform this marshaled into some wire representation, be it XML or JSON or what have you. You have the order, the types, the names. Pretty much all you need in order to know how to either generate the wire format or parse the wire format. All right, so I've sort of skimmed over this. Like we do have to generate some wire format, and we do need to send some output and read from input and parse that wire format into some M representation. Well, this is just generators, and this is just normal I/O. Like nothing is new here. If you could take something and turn that thing into some wire format, then you should be able to look at a marshaled and be able to do that as well. And once you've created a wire representation, be it a string or a byte array or a stream of bytes or whatnot, it's still the same old I/O. Nothing new there either. So I did just to sort of prove a point here, right? It's really difficult to create some sort of programmatic API for people to consume and do stuff with if I haven't tried it myself. So I took a weekend and just be very sure that I'm not a Jackson expert, right? I was basically diving into the how to Jackson. And I wanted to try to see if I can map marshaled to JSON and JSON to marshaled. And this code here works. And it was about 100 lines of code in the end to get Jackson to understand marshaled. And I can both generate and parse it. And I can also decide whether I want to embed the schema or I want to guess the schema based on the types or the number of the attributes, the names of the attributes, and the types of the attributes. So turns out that it's really trivial to take this structural representation and generate wire representation from that, using all the existing I/O stuff that we have in use, and going the other way back. So when we decouple concerns here, some of the design choices were use structure as data. How many of you are familiar with externalizable? Externalizable. Cool. Not many. It sort of had promise because this was a different take or yet another take on serialization, which is instead of describing your structure as data, you describe it as operations. So essentially, read this int, read this long, read this. And while that could work, it's really hard to reason about operations that you can't really introspect because they are locked inside some method somewhere. But structure as data allows you to introspect the data, to pass the data around, to translate the data. Another design choice was to, hey, okay, so this is nice, I can marshal a point. But what happens when a point also has points as a part of its structure? Or you can even imagine something like a collection where you have a collection of points. How does that work? Well, turns out that it's fairly simple to just say, let's just recursively marshal everything that we see. So when we marshal something, we get its data out, and then we look at the data and see, can I marshal that data? And just expand that into its marshaled representation, sort of creating a tree of marshaled instances. And then, of course, going back is just the inverse. Of course, it does have the trade-off that we don't support cycles, but as we've talked about before, cycles aren't necessarily good, and it's not necessarily something that is possible to reason about the correctness of by just reading the code. On the other hand, we're now wire format agnostic, so you could have a single class be used for both JSON, the old serialization format, or XML or whatnot, in the same application at runtime, because the representation is not tied to the wire format. We're also I/O agnostic. We don't care about I/O here. We just care about the structure. And what's interesting here as well is since we've divided up this monolithic serialization box into open-ended things, where we take responsibility for converting the point to the marshal of point, but then we leave it there. Now that's a surface area to add extra security to. So you have many different layers. You can have security filters and data corruption inspection, etc., both at the I/O level, at the wire format level, and have your typical validation rules inside your object as well. So you have multiple layers of protection. And also, we don't need to necessarily care about encryption and compression because those can just be inserted into the right steps of this pipeline. So another complaint was it's really hard to use correctly. So how do we fix that? I think the only real way of doing that is to just make it so simple that it's really hard to use wrong. So remove as much as possible in terms of added complexity, new features, etc., and let people program how they're used to programming, and just add the bare minimum to make this work. So for class authors, you just declare and define your entry and exit points. And you decide which entry and exit points should be exposed. So it's using 2 annotations and a single static method if you need it. So that's the sort of the added complexity from a new API surface. On the sort of the integration side, if you're a wire format library author that you want to take marshaled instances and turn those into whatever representation, you deal with marshaled instances. And you convert them into bytes or strings or whatever that is, and then you convert it back into a marshal. And we have some utility methods for that, of course. The main thing is the marshaled interface itself, but of course there are ways for you to introspect what is possible or what is being registered for a specific type. And that can be useful for ahead of time generation of marshalers or parsers, or generators or parsers. All right. I think it also speaks to making it dead simple that it's just recursive. Like you just expand it. Very simple. So if you have a new bar that has an int5 and a foo, and then you marshal it first to a marshal of 5 and the foo instance, and then you just look at the types and say, okay, I can marshal a foo, so I will turn this into a 5 and a marshal of foo. And simple enough, the same thing is on the way back. The only real trade-off that you're making here is that you can't necessarily stream it. You can't stream decode it, because you need to know what the innermost thing is in your tree before you can start populating it up. But that's not necessarily a drawback, because when you're descending that tree, reading it in, you could decide if you want to bail out early. Like I only go down so far into the tree, and after that I'm going to cut it off because I think this might be a malicious request or something. And also, if you do, you haven't done any of the work. You haven't loaded the types, you haven't done anything that you didn't need to do before you needed to do it. And this is also what record serialization does today. So since it needs to call a constructor, then of course you need to have the object that is going to be put in the constructor before you can create the record. So some of the design choices here. So want to have a really small surface area, build on top of existing features, no wizardry, no circularity, and a clear separation of responsibility. And I think the benefits that we see from this is, I think this is pretty easy to learn. There are very few moving parts using existing well-known constructs. It's very easy to use because there isn't that much to do. They're Marshall and unmarshal. It's really easy to reuse because you only need to define it once per type. And you don't need to have specific things for specific wire formats within the same thing. And there's also the ease of reviewability, because with serialization, it's really hard to review a pull request and be certain that it's doing serialization in a way that is both A, compatible with the previous version, but also B, is consistent between reading and writing it. So I think maintainability goes in hand with reviewability, because if it's difficult to review, it tends to be difficult to maintain. So the main takeaways here, we're trying to do a reimagination of serialization 3 decades down the road. We want to let class authors decide what their external data representations are via parameter lists as a primary means. And the important part there is you decide what the external format looks like. And since there's an annotation on it, in the future you can imagine that your IDE could list constructors and patterns that are annotated differently from other constructors. So you know what to choose. And you know what they're for. Interestingly, I think for most simple types, the same constructor will be used for both marshalling and typical construction of the object. And what's good about that is that it cannot get out of sync with itself. So you can't risk end up in a situation where your read object is different from your constructor. The responsibilities here are layered and clear. It's clear who's responsible for what, and it's also clear where you would inject different concerns in this pipeline. And what's good from a security perspective is that there are multiple points to make different kinds of validation and assertions. And the wire formats, they can consume and produce a unified structure, marshaled. That is how you interact with this. And as Brian said before, it does take a lot more time to arrive at something that looks like, why didn't you just do this from the beginning? This is like I've been looking. I think my current implementation of the entirety of this is like 1,300 lines of code, including documentation of everything. It's just like I'm not even sure it's a feature. I have to sort of pinch myself sometimes. So what are the next steps here? So I think we need to sort out the interactions between what we call marshalling now and what we have as a serialization. How should they interoperate? Should you be able to transparently serialize something marshalable? How do they relate, and how do you decide on what the primitives are? Because whenever you're going to send any data over, you need to have an agreed set of minimum structures. So is it ints, like the typical Java primitives, but is it string? Probably. Is it list? I don't know. The interesting point here is that it's not a binary decision. Marshalling recursively translates everything which is marshalable, which means that it leaves everything that isn't marshalable in place. So as long as the wire format understands those types and that data, they can still use it. And of course, this is a big one, right? investigate which JDK classes can support this and how it should be supported. And of course, yeah, the migration path, that's for sure. And of course, there's some details regarding the implementation, like performance-related things, and I won't mention any numbers here, but it's pretty fast on my machine. Famous last words. And last but not least, create a JEP from this and see what we can actually ship. So to just connect back to the theme of this is, it took a long time to get here, and I only spent like a year and a half walking down this mountain, but we did have quite a few opportunities where we could have left it more complex, and yeah, just make an effort.
Yeah, this had its own virtuous collapse, but it was 30 years after. So what Victor has showed you today is after we took out a whole bunch of stuff from the initial design that still seemed simpler than serialization. So what took you so long?
Yeah, I'm sorry. So we do have about 3 minutes-ish for questions, if anybody's...
And there's also the Ask the Architect session tomorrow if people have questions there. When you...
So clone, object.clone is a similarly magic method. Is this going to affect that? Is it going to apply to something like that?
Yeah, so the question is, what about clone, right? So right now, clone is implemented by magic. There's all kinds of warnings of don't use it, it sucks. If you have to use it like this, but it sucks, don't use it. But if you have a marshallable class, and it should be easy to make most classes marshallable, then cloning is trivial. You marshal it, you unmarshal it, and you get a clone.
Or you get the same object again.
Any other questions? Sir?
The collections.
Yeah.
You have an idea how you will handle the constructor and deconstructor for collections?
Yeah, so the question is, all right, how does this work with collections? And it works the same way as serialization does now. If you look at how collections are serializable, we serialize it by saying, okay, I am in linked list, array list, whatever, and now I'm just going to write all the elements of the collection into the stream. And then when I deserialize, I create an empty collection, and I insert elements into the collection that have come in from the stream. So we can formalize this and say the schema for marshalling a collection is just an array of elements. And the unmarshaller is a constructor that takes an array of elements. And what does that constructor do? Well, it creates an empty thing, inserts all the elements into the, and then it's done. And so it formalizes what is kind of a little bit magic, or at least subtle, in the serialization of collections, and just turns it into a dumb old constructor that takes an array and a dumb old pattern that produces an array.
Yeah, there's also the opportunity of just designing, I didn't show that in code here, but you can designate a static factory method to be the creation point. Yep. So in case of empty immutable list, you would always be able to get the single instance of an empty immutable list out of that factory.
Yeah. All right, we'll probably have time for one more question. Yeah, so the question is, what's the migration path for the use of serialization inside the JDK? And do we ever have a path to truly getting rid of serialization, is I think really the question you're asking. That's probably a long road. There's a bump in that road, which is compatibility. That one of the forms of compatibility that we pay attention to is serialization compatibility. And clearly, if you change serialization mechanisms, you're going to change serialized forms, and that might make some people grumpy. So we have to devise a gradual plan by which there will be some amount of time where some classes will use both marshalling and serialization, and then we start producing we keep producing the old format, but we are willing to deserialize the format from the future, and then in the next version you start producing the old format, and then eventually you turn off on marshalling of the original format. So it's likely to be a phased thing over time, but eventually we should be able to get there.
And we're good.
Yeah. Thank you very much.
Thank you.
All systems are nominal. Initialize Genesis